let's take a look at example 1. We're asked to find the following antiderivatives and to check our answers. So these are reviews of some basic techniques. Let's take a look at number 1 there. We're asked to integrate x squared minus cosine x dx. And this is meant to be a review of some of the basic properties and some of the basic formulas. So you may recall that integrals respect addition and subtraction. So I can use the sum and difference property to rewrite this as the integral of x squared dx minus the integral of cosine x dx. The first integral is a classic power rule. The integral of x squared dx, the power is going to get promoted. 2 plus 1 is 3. Divide by the new power, so x cubed over 3 minus the integral of cosine x dx, that's sine of x, and then to catch them all, capture all the antiderivatives, we tack on that c. Now the ultimate check to any of these problems is to start with your answer and take the derivative. We use the sum and difference property for integrals to get to our answer, so it shouldn't be surprising we need to use the sum and difference property of derivatives to check our answer. The first derivative here, I've got x cubed divided by 3. Don't jump to the quotient rule just yet. Dividing by 3 is the same as multiplying by a third. And we can factor that 1/3 out front using the constant multiple rule for derivatives. The derivative of sine of x is cosine of x. The derivative of a constant is 0. And now we can apply the power rule derivative formula for x cubed. That's going to be 3x squared. And the 1/3 multiplies the 3, cancels it out. I get x squared minus cosine x, which, by golly, that's the original antiderivative. So ideally, that's the best way. And I'm not going to work through the checks for all of these in this example. This is the best way. This is the perfect way for you to go through and verify them. However, we can verify them graphically as well using Desmos. And we'll be using Desmos quite a bit this semester. So how can we check this using Desmos graphically? Well, first off, we fire up Desmos on the website here. And we're going to type in the original integrand, x squared minus cosine x. And now we're going to type in the answer we got. I'm going to call it capital F of x, as is the custom for antiderivatives. And we arrived at x cubed divided by 3 minus sine of x plus c. And we'll add a slider for c. So once again, that's what all the antiderivatives look like. I'm going to click off the graph of my answer because all I really want is the derivative of my answer. So if I look at the capital F prime of x, as long as you're using x as the independent variable, Desmos will numerically calculate the derivative and then graph it. So there's the graph of the original integrand, the red parabola. Here's the graph, the purple, of the derivative. So this gives us a quick graphical check. Since the two graphs appear to be identical, this appears to give us verification that our answer is correct. So when I mention checking your answer using Desmos or checking graphically, this is the process I mean. All right, let's take a look at number 2. We're integrating function of u now, the square root of u times the quantity u squared minus cube root u du. And as you may recall, one of the things you, pun intended, learned in previous calculus is we can convert all of these radicals to powers and then deal with the exponents. So the square root of u is u to the 1/2 power, u squared minus u to the 1/3 power du. And we can distribute through here. All right? We don't have a rule yet for handling products products in terms of integration. But we can distribute here to avoid the product. We can do a little bit of algebra ahead of time. So this would be u to the 1/2 times u squared minus u to the 1/2 times u to the 1/3 du. And now I can do the product rule for powers. If you multiply with the same base, you add the exponents. So this would be u to the 1/2 plus 2. 1/2 plus 2 would be 1/2 plus 4/2. So that would be a 5/2 up there. Minus u to the 1/2 plus 1/3. Well, I'd have to convert that to 3/6 plus 2/6 to give me 5/6 du. Now we can apply the sum and difference rule. Integral u to the 5/2 du minus integral u to the 5/6 du. Going to add 1 to the power. 5/2 plus 1 is 5/2 plus 2/2. So I'm going to get a u to the 7/2. Dividing by 7/2 is the same as multiplying by the reciprocal 2/7 minus u to the, add 1 to this power, you're adding 6/6. That's 11/6 as the new power. Dividing by 11/6 is the same as multiplying by its reciprocal, 6/11. And then to capture all the antiderivatives, we tack on the c. And once again, the ultimate check here is to take the derivative, and then after you take the derivative, you're going to need to reverse all this algebra, which would involve factoring out and things like that. Now, if you want to check this graphically on Desmos, remember to check this graphically on Desmos for it to do the symbolic or the numerical derivatives, you're going to need to write all this in terms of x's. That would be your f of x, lowercase f of x, your capital case f of x, once again would be with the x's here. And then you would have a graph of the f prime. So when you do the calculus on Desmos, you're going to need to have the x there as the variable. Okay. Moving right along here to number 3, we're asked to integrate this quotient x cubed minus x divided by x squared. Dx. I'm just double checking here that I got the correct there. Now once again, don't jump over in the quotient rule. We don't have an integration formula that handles quotients unless the denominator is a constant, which it's not. So we'll once again going to do a little algebra here to help us. We can't help but see that there's a common factor of x both in the numerator and denominator. So we'll go ahead and do some algebra here to help us simplify a little bit to get going. So we can cancel one factor of x. X can't be 0 in the original integrand anyway, so we're not losing any information. And now we're going to do some more algebra, because if you have a fraction, the book calls this separating numerators, which sounds violent. But if you have fractions like this, really what's happening is we're distributing the factor. We're distributing the factor of 1 over c to both terms, but it looks like this. But this really is just distributive property again. So we can write this as an x squared over x minus a 1 over x dx. X squared divided by x we can simplify. And now we can use the sum and difference property of integrals again. So integral x dx minus the integral 1 over x dx. When x is written, we can think of that exponent there as being x to the first power. We can hit this with the power rule, x squared over 2 minus. If you write this as an x to the minus 1, and try the power rule, you're going to be in for a rough go because you'll try to be dividing by 0. This integrates out, as you may recall, to the natural log, absolute x, plus, of course, your c. Ultimate check, take your answer, take the derivative, reverse the algebra to get back to the original integrand. That's going to practice so much good math. If you don't have the time and you just want to do a quick check graphically, like if this showed up on a test or something, you can always use Desmos to check it quickly for yourself graphically. All right, let's take a look at number 4. I'm famous for stuff like this. Number 4, you've got very close to number 3, except now I've got this x, this plus 1 here in the denominator. So let's see what happens in this case. Once again, we don't have any properties of integration that deal with division. We can look at trying to factor. We could factor a factor of x out of the numerator. Ooh, we get close. We get an x squared minus 1, but it's an x squared plus 1. So we're kind of stuck with that. So one thing we can do is pull out long division. Because when you have a rational function like this, a ratio of polynomials, and the degree of the numerator, the highest power of x in the numerator, if that's bigger than or equal to the degree of the denominator, then that means that we can actually divide and rewrite this integrand. Think about this is very analogous if we had a fraction like whoops, what happened to my whoops, I don't want that. So if we had an improper fraction like 32 over 7ths, I'm adjusting here, something happened with the pen width. If I had like a 32 over 7ths, I could write it that way, or I could write it as a quote-unquote mixed number. 7 goes into 32 a total of 4 times. Well, let's I was thinking a little too far ahead. Let's do 31 here. There we go. With the remainder of 3. So I could write this as 4 plus 3/7. So 4 and 3/7. 4 plus 3/7. So this is kind of like what we have here. We've got an improper algebraic fraction, and we're going to rewrite it in this way. So the way we do that is we take the denominator here, x squared plus 1. More careful, as you may recall, in long division to put in the placeholders. Then in the numerator, we've got an x cubed plus a 0x squared minus x plus 0. Once again, careful to have the placeholders. And now we look here, we're looking at x cubed divided by x squared, or x squared into x cubed, depending on how you want to think about it. That goes x times. So I'm going to write that x here. And now I'm going to multiply x times x squared is x cubed, 0x squared plus x. And then, just like in regular division, I'm going to subtract. X cubed minus x cubed is 0. 0 minus 0 is 0. I have a minus x minus x minus 2x, and then bring down the 0. And now I look, x squared does not go into 2x because the power here is greater than the power there. So the power on top is less than the power on the bottom, so I know that that's going to be my remainder, like so. And so I can rewrite my integrand the same way I rewrote the improper fraction here. So thanks to that division, I can rewrite the integral x cubed minus x over x squared plus 1 dx as the integral of the quotient here, which is x, plus the remainder, which in this case is minus 2x. So a minus 2x over the divisor, x squared plus 1 dx. And using properties of integration then, That's the integral of x dx minus the integral of 2x over x squared plus 1 dx. The first integral we can handle using the power rule again. That's an x to the first power. So x squared over 2 minus, and you may need to use a u substitution, or you may recognize how this will fall out. You could let u equal x squared plus 1, so that your du is 2x dx. This gets you to a 1 over u du form, which is a natural log form. So this would integrate out to natural log absolute value x squared plus 1 plus c. But since the x squared plus 1 is always positive, we don't really need those absolute values in there. And we can write it like that. So once again, the ultimate check, start with your answer, take the derivative. The algebra here you would be getting a common denominator to rewrite the x minus 2x over x squared plus 1 as the original integrand. Or, once again, you could check it on Desmos. So long division. If the degree of the numerator is bigger than or equal to the degree of the denominator, think of it as like an improper fraction and divide it to rewrite it into something you can more easily integrate. All right. 5 and 6, we've got a couple of similar looking integrals as well here. The variable of integration is t. So I've got the integral 1 minus sine of t over cosine squared of t dt. And once again, we can use this. Once again, the book calls it separating numerators. We've got an a minus b over c, which we can write as a over c minus b over c. Once again, we're really just distributing 1 over cosine squared here. But we could rewrite this as a 1 over a cosine squared of t minus a sine of t over a cosine squared of t dt. And you should know anytime trigonometry is involved, there's a good chance we can make our life easier if we use identities. So here, the first term, 1 divided by cosine squared of t, well, that's 1 divided by cosine of t squared. So that's secant squared of t. That should ring a bell. Minus, and here we've got a sine of t over cosine squared of t. I could write that as a sine of t over cosine t times cosine t. I could write that as a 1 times a sine of t over cosine of t cosine of t. Or I could write that as a 1 over cosine of t times a sine of t over cosine of t, aka secant of t times tangent of t. And now using the sum and difference property, secant squared of t dt minus the integral secant of t times tangent of t dt. The integral of secant squared of t dt, that's your tangent of t. The integral of secant of t times tangent of t is secant of t plus c. And once again, to check your answer, take the derivative, rewrite using trigonometric identities, and then you do a little algebra to get back to the original integrand. If you do want to check this on Desmos, you need to switch out the t as the independent variable and switch in the x to check it on Desmos. Let's take a look at number 6. Number 6 is just the reciprocal of number 5. So here we're integrating cosine squared of t over 1 minus sine of t. And so we have a fraction that looks like this, which does not, quote unquote, separate. Okay? Separating numerators, once again, is a distributive property. I've mentioned it. I'll go ahead and write it out. Really what's happening here is you're looking at this as a 1 over c times a minus b and distributing. So separating numerators, once again, that's just a distributive property. There is no distributive property here because we've got a -1 power there on that quantity, whereas up here we have a 1 on that quantity. So that's the difference. That's why you can do one but not the other. So it looks like we're kind of stuck. Once again, it's a trigonometric problem, so we think about identities. And you may recall from the murky past, you can exchange cosine squares for sine squares. We'll be doing quite a bit of this here in the next day or two. Now what's nice about this is look what happens. This is now a difference of squares. I can factor the numerator using difference of squares. And now I can cancel from the numerator and the denominator. And look how nice this is. Now, of course, when I cancel this out, I'm assuming here that sine of t can't be 1. It couldn't be 1 anyway in the original. So it's not like I'm losing anything here. Use some indifference properties. The integral of 1 dt is t. The integral of sine of t dt is minus cosine of t plus c. So once again, take the derivative, reverse the algebra, do the trig identity, you're back to the start. Or you could check it graphically, assuming you switch out the t's for x's. So there's that. Folks, let's take a look at number 7 here. We're asked to integrate 1 over the square root of 25 minus 9x squared. Now, one thing you might do to get started is you might think, okay, well, let's convert this to a power. Maybe a 25 minus 9x squared to the minus 1/2 dx. Maybe you want to try a u substitution with that. Doesn't seem to get you anywhere. So just remind ourselves that we've got these basic formulas involving square roots and denominators, namely the inverse sine and the inverse secant have these sorts of things in the denominators. So if you try to rewrite a square root as a power and things aren't going your way, it might be because it's actually one of these inverse sine or inverse secant formulas. In fact, that's what's actually going on here. Now, the formula we get for the inverse sine is 1 over the square root of a squared minus x squared, minus u squared du. And it's really up to you, pun intended, how you want to do this. You can look at u as being 3x here. So we've got a u squared would be a 9x squared. What I like to do is I like to just factor out the coefficient of x squared here just to make things easier and avoid the substitution. So we're going to be using the inverse sine formula on this, but I'll show you how I like to deal with these as to avoid the u substitution. So what I'll do is I want to have a coefficient of 1 on the x squared. So I will factor a 9 out of the quantity. And remember, when you factor something out from a quantity, you're really dividing everything in that quantity by that number. So when I factor out a 9, I can do that. 25/9 would be left over. And you can do a quick check. If you distribute the 9 through, it cancels there. So that's fine. Now I can use the product property of radicals. 1 over the square root of 9 is going to be a 1 over 3 times the square root of what's left over. And that's a factor of 1/3 I can bring outside the integral. And I can think of 25/9 as 5/3 squared. And now I'm all set to use my inverse sine formula. I've got the 1/3 out front. It goes along for a ride. That's the scalar multiple rule. And then I have the inverse sine of x divided by this constant, So x divided by 5/3 plus c, and then I'll just sneak in the final answer up here. Because dividing by 5/3 is the same as multiplying by 3/5. This would be 1/3 inverse sine of 3x divided by 5 plus c. And once again, this is a wonderful example. Check your answer by taking the derivative. Check your answer by checking the graphs out on Desmos. Okay? So that'll do it there for number 7. All right, number 8, in the same vein, I mentioned inverse secant. We've got a variable squared minus a constant squared with the x out front. So this works out to be an inverse secant. We can proceed the same way we did with the inverse sine formula. Can factor out that 9. Product rule of radicals, the 9 comes out as a 3, which I can factor all the way out front since it's a constant. And we can rewrite the 25/9 as a 5/3. So I get myself the 1/3. This is going to be the, now for the inverse secant formula, I'm going to have a 1 over the 5/3. So 3/5 again times the inverse secant of the absolute value of x divided by the 5/3. So that would be a 3x over 5 plus c. And the 1/3 multiplies the 3/5. That's going to give you that 1/5. And so I get a 1/5 inverse secant of. Now the 3 and the 5 are positive to begin with, so I just need to get that x in absolute values. So 3 absolute value x all 5 divided by 5 plus c. And there's our answer to that integral. All right, moving on to number 9. We're looking at the integral of 1 divided by x squared minus 2x plus 10. And once again, we talked about this previous example. Fractions don't work this way. Okay, you can't break the fraction up that way. We don't have anything that's got quadratic in the denominator except for inverse tangent. So if I look at inverse tangent, I've got a sum of squares down there for inverse tangent. And in fact, this is an inverse tangent. We just need to complete the square. So let's talk about completing the square. So basically the idea is if you have x plus h quantity squared, you have x squared plus 2hx plus h squared. And you can think of this as a nifty little geometric problem as well. If you have x and then h by x and then h, then that part's there is your x squared. Here's a rectangle measuring xh. Here's another rectangle measuring xh. And here's your h squared. All right. So when we look at x squared minus 2x, we can think of that as being the start of this perfect square trinomial. And so the question is, what do I have to add to get this to work? Right? So whatever's out front, this coefficient, that's your 2h. So 2h here would be a minus 2, so h would be a minus 1. And so we would need to add in minus 1 squared to complete the square. but then we would have to subtract that off to keep the balance the same. So then this would factor, perfect square trinomial, x minus 1 quantity squared minus 1. That would be the same as x squared minus 2x. Okay? Or we can think of it as we're going to take a 1 from the 10 to get that perfect square. Either way. The long and short of it is that here's an integral I don't know how to do. By completing the square, I get to an integral I do know how to do. So I can think of 9 as being 3 squared. If I need to go through the formal u substitution, I would let u be x minus 1, du is dx, or I can just apply that principle of linear substitution there on the front page. I could do that as well. No matter how you slice it, you're going to get an inverse tangent form, 1/3 inverse tangent x minus 1 over 3 plus c. So in general, for completing the square, if you've got something that looks like x squared plus bx, then the completed square version of that would be x plus b over 2 quantity squared minus b squared over 4, or, b over 2 quantity squared. That might be a better way to think about it. So if you took the time to multiply this out, you'd get your x squared plus bx plus b squared over 4 minus b squared over 4. That gives you that. So this is how you can go in and complete squares. All right. So let's take a look at number 10. Number 10 looks like a complete nightmare. But once again, completing the square is going to help us with number 10. But this looks terrible. It's minus 9x squared plus 36x minus 11 dx. And once again, the first thing you might try is rewriting this as a power, letting u be what's in parentheses, but the du is nowhere to be found. So in fact, this will work out to be an inverse sine formula, which has a radical in the denominator, if we complete the square. So let's look at trying to complete the square here. Let's just look at the x squared and x parts. Now to get going, to use this nice formula here for completed squares, I need the coefficient of x squared to be 1. So let's go ahead and factor out that negative 9. So if I factor out the negative 9, I'm left with this. And now I'm just going to replace the x squared minus 4x using the recipe. You cut this in half, x minus 2 squared. You square that, would be a plus 4, so to keep the balance it would be a minus 4. So if you want to follow the formula, the b here is a negative 4. So the b over 2 would be a negative 2. So there's the b over 2 there, and there's the b over 2 squared going into there. So that's the formula there, if you've forgotten it from algebra. So this is going to be a negative 9 times the quantity x minus 2 squared plus 36. And now I'll substitute that back into here. So now the integral I have to contend with is going to be a negative 9 quantity x minus 2 squared plus 36 minus 11 dx. And what you can see here, this is going to be nice. This is going to work out to be 25. So that's going to be 25 minus 9 x minus 2 squared dx. And at this point, you say, okay, this is looking like the inverse sine formula. I do have that 9 in there. I'll factor the 9 out, just like we did previously. I'll get that 1/3 out front like we did previously. And 25 over 9, that's 5/3 squared. Now if you need to, you can go through the u substitution if you want. Let u be x minus 2. So the du is equal to the dx. Or you can just use that principle of linear substitution. What do we get? We're going to get that 1/3, went along for the ride. We're going to get the inverse sine of x minus 2 divided by 5/3. So we could write that as 3 times x minus 2 over 5 plus c. Check your answer, taking the derivative, multiplying things out to reverse the completing the square process. You should get back to your original integrand. And that'll do it for example 1.